In this video, we're going to talk about what the definition of a rational function is and use this definition to determine whether certain functions are rational functions. And to understand rational functions, we first need to understand what a polynomial function is. And in general, polynomial function is going to have this structure that we listed over here for p of x. It looks really complicated, but all that goes down to is that for every term of the polynomial function, we would have some coefficient times x to a positive whole number power. And this is a standard form of a polynomial function where the power of or exponents of each term is decreasing. So it starts from n and goes down to n minus 1, etc. And in this case, the coefficients a sub n minus 1, etc., these can be any values that we want over here as long as it's a real number, and the exponents, as we define, we need it to be a positive whole number at all times for it to be a polynomial. So that just tells us x cannot be in a denominator and the exponents must be whole numbers. We can't have fraction exponents which would give us roots, and we cannot have absolute values for the variables. So basically we're just having each term to be x to a whole number power, multiplying by some coefficients, some constants over here. And we can do addition and subtraction between these terms because these coefficients can be positive or negative. And once we understand what a polynomial function is, a rational function just means we're taking the quotient of two polynomial functions. Both the top and bottom of a rational function must be polynomial functions. And that's the standard we're going to use to determine whether something is rational or not. So let's take a look at some examples over here. For number 1, we have n of x. And anytime you're looking at a function, we first want to decide whether there's any different terms that doesn't follow the requirements we have for terms of a polynomial function. And right away I see that we have square root of x. It's not going to be x to a whole number power. Because of this is not a rational function. And now for part 2, we have this expression over here. Everything on the numerator is good because the numerator is indeed a polynomial function. But now if we look down to the denominator, we see that we have x to a negative 7 power. Remember, we said the power must be a positive whole number, so it's saying no, this is not a rational function either. And next, for number 3, if we look at the top, this is the same as what we had before in number 2. So we know this is a polynomial function. And now looking at the bottom, we have 3. This might be a little bit tricky to think about, but indeed this is a polynomial function, because when you think about it, we just have all the other coefficients to be 0 and our a naught as a last term, that constant term, being 3. And as a result, we say this is indeed a rational function based on our definition. Looking at number 4, the top, again, we can check it is a polynomial function, but we should notice that we have x to a 0.7 power, which is not a whole number power over here, so this is not a rational function. Now for number 5, one thing that should jump out right away is that absolute value of x. And we specifically said x cannot be in the absolute value, and that's where we identified that. And we can say this is not a rational function. Now lastly, for number 6, the denominator, as we can see, is a polynomial, and on the numerator this might be a little bit interesting to look at because we do have a square root of 7, but all the powers for the variables are actually positive whole numbers. And when we consider that, this square root 7 actually doesn't affect anything because we said the coefficients can be any real number as long as the variables are not under the roots. So this, even though we have a square root of 7, this is still a rational function over here because it doesn't apply to the variable that we have. And that's how we determine whether a function is rational or not.